So our next presenter is Salim Masoumi. The title is Multi-GNSS Orbit Solutions from the third IGS reprocessing, and Salim joins us from Geoscience, Australia. He's our new IGS Analysis Center co-coordinator. So thank you very much for being here this morning. And 1 second.
I stopped sharing.
Oh, thank you. All right, Salim, and you have the floor.
Okay. Thank you very much. I think you can probably hear me now.
Yes,
right?
perfect.
Thank you very much. Today I'm going to talk about the status of the multi-GNSS orbit solutions from the third IGS reprocessing. I would like to acknowledge Michael Moore, who was the previous IGS analysis co-coordinator, and he handed over the role to me in the last or the one before IGS governing board meeting. I'll start with the IGS, different types of the IGS products. So in addition to the broadcast, ultra rapid and final products, the IGS performed a reanalysis of the historic GNSS observations with the latest refinements in the models and standards every few years. For the Repro 3, in total, 10 analysis centers contributed to the reanalysis by submitting different sets of products of the station position, satellite orbits, station satellite clocks, satellite attitude and biases as orientation parameters and troposphere. This was following the analysis centers workshop in 2019 in Potsdam, where the analysis centers agreed on a set of recommendations for the analysis techniques and modeling strategies. However, the analysis centers may still use different models and techniques on different sets of observations based on their own preference and capabilities. Therefore, the submitted products are not fully consistent with each other. 9 of the analysis centers submitted orbits. As you can see in this table, all of the analysis centers submitted GPS satellites orbits, while some also submitted GLONASS and GALILEO. So this famous figure again. So the current traditional orbit and clock combination software has been providing combined products for over 20 years. So as you can see in this figure, which is the weighted RMS of the final orbit since around 1994. So the algorithm used by the current software is based on a robust technique which tries to minimize the absolute deviations of the individual orbits with respect to a weighted average of the orbits. The produced orbits using this approach has proven to be very reliable for use in the precise positioning science applications. However, the current software is not designed to handle the multi-GNSS and is limited to GPS only and GLONASS only combination. So in order to move forward to the multi-GNSS, there was need to upgrade the software to allow for this capability, and this was our motivation to develop an upgraded combination software that can handle multi-GNSS combinations. This new software is still based on the same robust weighted average technique by the current software. However, new ways of weighting the orbits are added into the software. So just a quick rough flowchart of the orbit combination process. The orbits from different analysis centers or ACs will first get transformed using the transformation parameters from the terrestrial frame combination, which was which was performed by Paul, as well as with the AC ERPs. So in order to, in an attempt to make them align them into a common reference frame. Then a simple mean of the orbits is performed, and each AC is transformed to the frame of the mean orbit, and AC weights are calculated from the absolute deviations with respect to this mean orbit. So here is where the new software will has a different or an additional ways to weight the orbits, the ACs. So the traditional weighting approach has been the what I call the global weighting, where each AC is weighted based on the absolute deviations with respect to the mean orbit over all the satellites. However, the satellite-specific weighting, which is another weighting which was added to the new software, performs a weighting for each AC based on individual satellites. So each AC gets a different weight for each satellite. This weighted, AC weights then help us to do a weighted mean of the orbits, and the RMS and transformations of each orbit with respect to this weighted mean are calculated. These are used in an outlier detection process to exclude any satellite or AC which have RMSs or transformation parameters above a set threshold. And this process is iterated until there is no outliers. Then eventually each AC orbit is again transformed to the frame of the weighted mean orbit, and finally the weighted mean of the transformed orbit will be the final orbit, final combined orbit. So we now look at some of the statistics from the orbit combinations from the repro 3. We first have a look at the median satellite RMS for each AC with respect to the combined orbits for different GPS satellites for the years 2013, 2014, and then 2019 and 2020 as well. The x-axis in these figures are the satellite vehicle numbers, SVN, and the y-axis are the name of the analysis centers submitting the orbits. With the block codes 2A, 2R, 2F3, showing which block each sets of satellites belong to. For 2013 and 2014, we also have the comparison to repro 2, which is shown by IG2 in the second bottom rows, and shows a consistency of usually around 5 to 10 or 15 millimeter with respect to the repro 2 combinations for most of the satellites. We also have the IG3 solution in all of the figures, which shows the comparisons to the GPS-only combined orbits from the traditional software. The median RMS for the GPS satellites in a multi-GNSS combination, which are these results, matches very well with the GPS-only traditional combination with RMS of usually around 1 millimeter. Looking at these figures, you can see how for some of the centers, for instance, the RMS is smaller, for instance, for block 2R satellites compared to the other blocks, while some other centers are more consistent across this blocks, which could be due to the different solar radiation pressure models used, but needs to be further analyzed. Also, it is clear that there have been improvements in the RMS values for blocks 2R and 2F over time, and block 3 satellites in 2020, you can see, are the most recent, and hopefully they will also improve over time. So the caveat in assessing the RMS statistics, just to point out, is that they only show how well each orbit solution agrees with the combined mean orbit, and does not necessarily show how accurate the orbits are. So looking at the same RMS statistics for the GLONASS combinations from 2017 to 2020, The RMS values are generally much larger for GLONASS, noting that the scales are now changed from 25 millimeters to 50 millimeters, the scales on the plots. The more recently launched GLONASS satellites have much improved RMSs compared to the older Block M satellites. One other thing to notice here is how some of the centers can have very different RMS values with respect to the combined orbit for different satellites. For instance, TUG has been doing really well for the GPS and for most of the GLONASS satellites, and also for Galileo, as you will see in the next slide. But for a few of the GLONASS satellites, the TUG is not one of the lowest RMSs. So this might indicate a necessity for using a satellite-specific weighting method as compared to a global weighting method for such satellites. Looking at the same RMS statistics for the Galileo is interesting because as we go from 2017 to 2020, the number of satellites in operation has been increasing. Also, the RMS values of the satellites have been improving a lot over time, which is really encouraging for Galileo. So looking at the trend for the overall combination for the overall satellite orbit RMS statistics, overall combination RMS statistics, over time for one orbital plane from each of the three constellations as examples, we can see this obvious improvement in the RMS from 2013 to 2020 for Galileo, the top right figure, which reaches the RMS levels of comparable to the GPS ones in the more recent years. And this shows the potential for the inclusion of the Galileo in the operational projects. So the shaded regions in these plots are the periods where satellites experience eclipse caused by the shadow of the Earth or Moon, which is generally the cause for the mismodeling of the satellites as the solar radiation is lifted, and there are also satellite attitude control issues. So going back to the discussion about which weighting approach to use. So here is a comparison between the use of the global weighting and the satellite-specific weighting for one plane A of the GPS. So if you look at the figures, you can see that there looks to be a slight reduction in the overall RMS of the satellites with the satellite-specific weighting, especially for one of the for some of the satellites which have been not doing very well, like SVN 38 or 39. And you can see these reductions in the median RMS values. The similar reduction in the RMS can be seen for the Galileo, but it is much more clear for a couple of GLONASS Block M satellites, SVN 730 and 734, where you can see that the RMSs are clearly reduced a lot with the satellite-specific weighting. So what we can do is to have a look at the weights given to each orbit solution to see what went wrong with the global weighting. Yeah. So here on the left, you can see the percentage of weight given to each AC orbit over time, which is quite consistent over time from 2013 to 2020, generally speaking, for all the ACs. One point to notice here is that this weighting for the Repro 3 actually is only based on GPS, because not all the AC solutions have all the three constellations, GLONASS and Galileo. Not all of them have the GLONASS and Galileo. So basically, GLONASS and Galileo satellites have no role in deciding how they are being weighted. So looking at the figure on the right, this is a typical GPS, typical healthy GPS satellite SVN45, the weight percentage of the weights with the satellite specific weighting. And you can see that still it's more or less comparable to the weights given to by the global weighting. However, if you look at one of the problematic GLONASS satellites, SVN734, you can see that first of all the weights for each AC for this satellite have been changing over time quite a lot, and very much different from what weights are given to the ACs as a result of the global weighting. And again, this is because this has two reasons. The first is that only GPS has been used for weighting all the satellites in the global weighting. And also because the ACs perform differently for different satellites based on what models they use, which is more evident for GLONASS satellites, but is still true for GPS and Galileo. And looking ahead for the inclusion of Baidu, for instance, they have geostationary and MEO satellites with different characteristics that could show these variations even more in the future. So to conclude this weighting discussion, the traditional global AC weighting is only based on GPS, which may compromise the robustness for the GLONASS and Galileo. The satellite-specific AC weighting helps maintain the robustness of all the multi-GNSS satellite orbit solutions. However, there may be concerns about the satellite-specific weighting not preserving the internal consistency of the AC orbit solutions, because they are basically using different weights for different satellites within each AC. The preliminary tests have not yet shown a significant impact on the PPP results as a result of the satellite-specific weighting. However, more PPP analysis can be performed. I think Simon maybe and Jian Hui will have some of their PPP results using some of these orbits, but we haven't seen a very significant impact, but we should do more analysis about that. Constellation-specific weighting may be regarded as an approach in between. However, given the different modeling issues of the satellites, even within each constellation, particularly for GLONASS, this does not resolve all of the issues. We have been only relying on RMS statistics for these analysis. So validation of the orbits with satellite laser ranging observations can be a great tool to assess the weighting approaches. This was performed previously by Christoph Sosnica for our experimental multi-GNSS combination. So this, I think, and a similar analysis would be really helpful in these. In deciding which weighting approach to move forward. However, the bottom line for the Repro 3 to be pragmatic as well as not compromising the quality is that we are planning to provide 3 different sets of solutions for the orbit combinations from Repro 3. What we call IGS 0, which is the traditional GPS-only combined orbits using the traditional current software. This is exactly similar approach to what was done in Repro 2, and this is only GPS only. Potentially, we can have the GLONASS only and Galileo only using an adapted version of the same software. Then we will have the IGS-1 orbits, which are the multi-GNSS combined orbits using the traditional, still using the traditional global AC weighting algorithm. And then there will be IGS-2 orbits, which are the multi-GNSS combined orbits using a satellite-specific AC weighting. You can consider this one as a development product, or just we can have more analysis on them, and then users can decide which one they want to use. So for final remarks, the Repro 3 combined orbits, in an answer to one of the questions, are planned to release by about November this year. It could be much sooner than that, but we just don't want to compromise the quality of the published orbit. So I would say around November this year. The future direction after the Repro 3 is first of all the switch of the operational products to the Repro 3 standards. Multi-GNSS inclusion for the operational products. A few of the analysis centers are already submitting multi-GNSS products in their operational products. So we will pursue this and try to initially include the multi-GNSS products as in parallel to the standard products as an experimental set of products, but eventually switching to fully to the multi-GNSS, as well as switching to the use of the new combination software once all the validation steps have been taken. So yeah, thank you. Happy to answer any questions.
Yes, thank you very much, Salim. We're almost out of time for, we have to move to the next speaker. However, there's a question by Jim Ray on the Q&A. Again, you can type the answer on the chat and then we can revisit these at the end of all the presentations. Thank you very much, appreciate it.